Discussion session. See, in the previous video, we discussed multiple choice questions from the chapter Dual Nature of Matter and Radiation. And in this lesson, we are going to discuss 2 and 3 mark questions. A few 2 mark and 3 mark questions from the same chapter, Dual Nature of Matter and Radiation. Okay. So let us start with the question number 1. How does Einstein's photoelectric equation explain the emission of electrons from a metal surface? Explain briefly. See, we have to explain the photoelectric emission based on Einstein's photoelectric equation. We know, see, the first part of the question. See, that was the first one, okay? A part, and see the first part of the question. This is the second part of the question, which is a graph. We'll come to that after completing the first part of the question. See, Einstein's photoelectric equation, we know it is the maximum kinetic energy of emitted electrons, Ke, is equal to the energy of incoming radiation, right, minus work function of that particular metal, photosensitive material. See, this is the Einstein's photoelectric equation, and our explanation should be based on this one. And we know Einstein explained, the points we have to include in the answer, Einstein explained photoelectric effect using photon theory of light, correct? Particle nature of light. We know photoelectric emission is a phenomenon which can be explained only using particle nature of light. So, photon theory of light, that is what the first point that we have to include, the mention that term, right? Einstein explained photoelectric effect using photon theory of light. Okay, one more point in which, using which he explained photoelectric emission. In that explanation, he explained photoelectric emission as a particle-particle interaction. Particle-particle interaction in the sense, what do you mean by that? Which are the 2 particles we are talking about? One of the particle is photon. See, one of the particle here is photon. And the second particle is electron. Yes. And he explained whenever a suitable frequency of radiation, a radiation of definite suitable frequency incident on a metal surface, electrons are emitted from it. That phenomenon is called photoelectric emission, we know. See here, the 2 particle interaction is like, one is photon, the basic building block of light, right? According to the photon theory of light, there is a basic building block. So that is one of the particle interact with another particle, that is the electron on the metal surface. So when this particular particle, that is photon, collides with electron, the entire energy of electron, that photon is transmitted to electron. See, energy of photon, incoming radiation, is transmitted to the electron on the metal surface. See, when electron get enough energy from the metal surface, it will be ready to come out of the metal surface. It will be ready to be free from the atom, right? That is what happens. And he says that energy of incoming radiation, which is denoted by E, is equal to h nu, where nu is the frequency of that particular radiation, or which can also be calculated as hc by lambda. That energy is given to electron. Then electron will use that particular energy for 2 purposes. One is to be free from the metal surface, right? To be free from the metal surface. For that, it requires an energy which is equal to the work function of the metal surface, that particular photosensitive material. And if there is enough energy, if excess energy is there, that will be used as the kinetic energy of electron. That is how Einstein obtained the relation like h nu, the incoming frequency, incoming energy of the incoming radiation is equal to kinetic energy plus the work function. Correct? That is how we got kinetic energy, maximum possible kinetic energy of emitted electrons is equal to h nu minus work function. Okay, so this is how we got the Einstein's equation, and this is the answer for the question. So it is a 2 or 3 points you have to include. One, I told you, photoelectric emission is explained using photon theory of light. Yes, in which Einstein explained photoelectric emission as a particle-particle interaction. Photon and electron. Photon of incoming radiation, electron on the metal surface. That interaction, that is particle-particle interaction. And then, see, this is how they interact. Energy of photon will be given to electron. Electron use that energy for 2 purposes, and photoelectric emission happens. Right. Now, what was the second part of the question? Second part of the question is to plot a graph. Plot variation of photocurrent. Okay, we know photoelectric current is the current constituted by emitted photoelectrons. Yes. With respect to, we have two cases given. First one with respect to the collected plate potential. So applied potential versus photoelectric current graph. We know how to draw this. And remember, for different intensity of incident radiation, keeping frequency be the same, we are going to change different intensities. So at different intensities, what will be the graph? That is the first case. Second one, intensity of incident radiation and photoelectric current. So two graphs we have to draw. So we'll go for the first one. First one is the photoelectric current and applied potential graph. We know we have taken accelerating potential along positive x-axis and retarding potential along negative x-axis. Photocurrent along y-axis. This is how we draw the graph. And we have found in the experiment, even at zero applied potential, we had some non-zero photocurrent, right? Because some of the electrons were enough, they have enough kinetic energy to cross the distance by themselves. We know the concept. So from there, when you increase the accelerating potential, photoelectric current also increases, and finally it comes to a saturation stage, right? A saturation current. This is how we represent intensity. Suppose this is for an intensity I1, how will you complete the graph? It comes to this side, right? That is how we can just draw this graph. This is the stopping potential, we know, V0. This is how the intensity, photoelectric current changes with respect to potential. And you're asked to represent for different intensities. So just draw one more graph and we can write what is the relation between those intensities. So I'm going for one more graph for another intensity. See, I2 is greater than I1. That's what I'm going to do. If I2 is greater than I1, definitely this current will be more than the first case. See, this is the graph for second intensity if I2 is more than I1. Suppose I2 is less than I1, that graph will come below that graph of I1, we know. And on the other side, see, we keep the same stopping potential because there is no change in intensity. There is no change in frequency. You're asked to draw it for different intensities only. So this is the relation. This is the graph required. Okay. So accelerating potential versus photoelectric current graph. Now, the second question was to draw a graph for intensity and photoelectric current, which we know. See, that is a straight line. So if you go for intensity of incident radiation and photoelectric current, we know how to draw the graph. That graph is a straight line, right? That is how they are related. And that graph should start from the origin because non-zero intensity, a zero intensity means zero photoelectric current, correct? Whenever there is a non-zero intensity incident on the metal surface, at the moment onwards, current starts to flow. So it starts from zero, right? The graph starts from zero, a straight line because intensity and photoelectric current I is directly proportional to intensity. So the graph will be a straight line. So this was the answer for the first question. Okay. Let's move on to the second question. Figure shows the variation of photoelectric current measured in a photocell circuit as a function of the potential difference between the plates of the photocell when light beams A, B, C, and D of different wavelength are incident on the photocell. Examine the given figure and answer the following questions. Okay, so the questions are based on the given figure. You have given a figure along with the diagram. Look at this. We have applied potential along x-axis, the same graph which we have drawn for the previous question. See, photoelectric current along y-axis and applied potential along x-axis. So then we get four different graphs are given. Graph A, B, C, and D. Now the questions will be based on this, of course. Let's go through the questions now. Which light beam has the highest frequency and why? So out of these four, which light beam? See, A is a light beam, B is another one. So these are the light beams given. Out of these four, which one has highest frequency? And how will we identify the one with maximum frequency from the graph? We know stopping potential, right? Stopping potential is proportional to frequency of incident radiation. Stopping potential is proportional to frequency of incident radiation. Greater the stopping potential, that particular graph represents for the beam which has maximum frequency, correct? Yes. So in the previous graph, we explained the same. See, this was the stopping potential, right? So if stopping potential is more, that means that particular wave has more frequency, that particular radiation has more frequency. So here, if you check the stopping potential, this is the graph B, okay, sorry, C. For C, this is the stopping potential. And look at this, the graph D is this one. Then this is for graph A and this is for graph B, okay? Closely observe the graph given and identify what are the meeting point on the x-axis. There you can find out what is the stopping potential is. Now, you're asked to find out beam which highest frequency. Highest frequency is the one which has highest what? Stopping potential. See, highest stopping potential is for the beam B. So, answer for the first question is B. Because that particular beam, from the graph, that particular beam represents maximum stopping potential, you know. That is the explanation. You're asked to identify that wave and you're asked to explain why. No? Yes. So that part is fine. Easy. Look at the second question. Which light beam has the longest wavelength and why? See, longest wavelength is actually going for shortest frequency, right? Least frequency. Correct? Longest wavelength stands for least frequency. Frequency and wavelength are inversely proportional, we know. Yes, so if wavelength is the maximum, frequency will be the least. Now we can already, we know how to find out that from the graph. The one which has least frequency will have least stopping potential. So which one represents least stopping potential? That is for C, correct? The graph C gives you the minimum, least stopping potential. So the second question, the answer is C. This was B and this is C, because that gives you minimum stopping potential. That is what we have to explain there. Okay, now which light beam ejects photoelectrons with maximum momentum and why? Okay, see here we have to find out maximum momentum. Maximum momentum, we can relate kinetic energy and momentum, right? Momentum is directly proportional to the kinetic energy. We have the relation kinetic energy is equal to P square by 2m, correct? Or P is equal to root of 2m into kinetic energy, that relation. Yes, so from that we can say kinetic energy is directly proportional to momentum. So the maximum momentum transition or maximum momentum beam will have maximum kinetic energy, correct? Maximum kinetic energy. And kinetic energy is proportional to what? Kinetic energy of photoelectrons is directly proportional to the frequency. That also we just mentioned before, right? Kinetic energy proportional to frequency. So basically, we can say you have to find out the maximum momentum one. Now, momentum is directly proportional to frequency. Because momentum is proportional to kinetic energy and kinetic energy is proportional to frequency, we can say momentum is directly proportional to frequency. And which one has the highest frequency? We already identified. That is for the graph B. Okay. So that is how we identified the beam corresponding to each and every question. Okay, next one. What is the effect on threshold frequency and stopping potential on increasing the frequency of incident beam of light? Justify your answer. Another 2-mark question. See, incident beam of light, frequency of incident light. I am going to change the frequency of incident light. How will that affect threshold frequency and stopping potential? See, we know it's an easy direct question. See, if you go for threshold frequency, see, threshold frequency is actually constant for a given photosensitive material, right? A given photosensitive material has a work function W0 is equal to H into nu naught. W0 is constant for a given photosensitive material, which is calculated as H into nu naught. See, nu naught is a constant. Whether you change the frequency of incident radiation or intensity of incident radiation, that won't affect threshold frequency at all. So it's a constant. So the answer for this is no change. because it is a threshold frequency is a constant for a given photosensitive material. Yes. What about the second part of the question? You're asked to check what happens to stopping potential. Yes. So another quantity we have to check is stopping potential. So what happens to stopping potential if frequency is increased? See, we already explained that concept in one of the previous questions. So we know stopping potential is directly proportional to, right? Proportional to the frequency. So if you increase the frequency, what happened to the stopping potential? See, frequency is increased. So stopping potential is also increased. Therefore, stopping potential is also increased. That is the change, right? Okay, so that was easy, right? Next one. Calculate the wavelength of de Broglie waves associated with a proton having 500 by 1.673 electron volt energy. How will the wavelength be affected for an alpha particle having the same energy? See, don't be scared by looking into the values given, right? Actually, they helped you by giving these kind of values, which will simplify our calculation. Okay, that will make it easier. Let's see what is to be calculated. We have to calculate wavelength of de Broglie waves, like de Broglie wave associated with a proton. And its energy is given, kinetic energy is given. So, like we discussed in the previous session, like, we had a discussion about de Broglie wavelength in the other video, right? Yes, in detail, like which are the different forms of that equation and all. So, here kinetic energy is mentioned. Therefore, lambda is equal to h by root of 2me is the possible equation we can go for. Not only that, it is a charged particle, it is a proton. So, we prefer the other equation, which is h divided by root of 2m into, okay, fine. So, we don't need this equation because only kinetic energy is mentioned, right? Not stopping potential. So, this equation is enough. We can go for this equation. Yes, in which h is the Planck's constant. What is m stands for? M is mass of the particle given, mass of proton. Okay, mass of proton will be given in the question paper. You can cross check. In the beginning, we will be given a list of constants. There it will be given, or most of the time it will be given along with the question if it is not there in the beginning. Okay, so mass of proton is 1.6728 or 1.673 into 10 raised to minus 27 kilogram. That is the mass of a proton. Okay. Then what else is needed? Energy. Energy is given. Energy of proton is given in the question, that we can substitute there. And h is the Planck's constant. That also will be given, right? 6.6 into 10 raised to minus 34 joules second. So all values are there. Direct substitution and simplification. See, let us check the first part of the question. A is to find out for proton. Later in the second part, you're asked to find out what will be the change instead of proton if we use an alpha particle. Okay, so we'll come to that later. Let us find out the first one. Lambda is equal to, see, h is the Planck's constant, 6.6 into 10 raised to minus 34 divided by mass, square root of 2 into mass is given, I told you, 1.673 into 10 raised to minus 27 into what is energy value given. Look at this. Energy value is 500 divided by 1.673. Wait, hold on. See, we use it mass in kilogram, right? Mass in kilogram. Planck's constant we substituted in joule second. That is also in SI unit. Then we need energy not in electron volt but in joules, right? The SI unit. So we have to convert this by multiplying with 1.6 into 10 raised to minus 19. Now it is converted to joules. See, this is the equation. We substituted all the values. Now look at that. We can cancel 1.673 directly from there. That is why, see, this value is given in accordingly. Correct? That's why I told you don't be scared by looking into that particular value. That makes the calculation actually easier. Now, look at this. 2 into 500 is going to be 1000. So, 1000 into, we have 1.6 into 10 raised to 27 and 10 raised to minus 19, right? So, 10 raised to minus 27 into 10 raised to minus 19. Sorry, that is the whole square root. And on the top, we know it is h. H is 6.6 into 10 raised to minus 34. Okay, so fine. So we can now simplify this. 6.6 into 10 raised to minus 34 divided by square root of, see, 1.6 into 10 raised to, like we can say 10 raised to 16, right? 27 and 16, we get 43 into 10 raised to minus 43, right? And look at this, 1.6 is not a perfect square. We can say 16 is a perfect square. So I'll rearrange this into, see, 6.6 into 10 raised to minus 34 divided by 16 into, see, if you multiply with 10, divide by 10. So 16 into 10 raised to minus 44, the whole square root. Now look at to the denominator. We have 6.6 into 10 raised to minus 34 divided by 16 is going to be square root 4 and 10 raised to minus 22. 10 raised to minus 22. So we get 6.6 divided by 4 into 10 raised to minus 12. Correct? And 6.6 by 4 is going to be 3.3 by 2, which is 1.65. So 1.65 into 10 raised to minus 12 meters. That is the wavelength required. Okay, see, calculation was very easy. We didn't even use any multiplication or division. It was simply cancelling, and we simply like without even any calculation we could simplify that directly. Yes. So that is the answer for the first question. De Broglie wavelength associated with a proton is 1.65 into 10 raised to minus 12. Wait, we have a B part of the question. What's the B part of the question? How will the wavelength be affected for an alpha particle? If it is an alpha particle, how will this wavelength be changed? Okay, see, if you go for an alpha particle, which of these quantities are going to be changed? Lambda is equal to h by root of 2me. See, we are going to consider the same energy as per the question. Only difference is in mass, right? If it is a proton, we know mass of proton is just 1 atomic mass unit, but mass of alpha particle is going to be 4 atomic mass unit, correct? 4 atomic mass unit. So that will be the only difference. If it is an alpha particle, this becomes, see, lambda of alpha is going to be h by root of 2 into what? 4 times m, right? 4m into E. That is the only difference. If m is mass of proton, what will be mass of alpha particle? 4 times of that. If you take that 4 out, it will be square root of 4. So it becomes 2. So h divided by like 2 into, we get root of 2me. Correct? Yes. See, look at this. This quantity already we have found out. What is it? Lambda of alpha particle is equal to, this is lambda of proton, right? The one which we calculated before. So lambda of proton divided by 2. So the wavelength reduces to half of the value if it is a part like alpha particle instead of proton, because the mass will be 4 times of the mass of proton. Okay, fine. So that was the question. Now let's move on to the next. Yeah, the figure shows Vm square versus 1 by lambda graph for photoelectrons emitted from the surface, where Vm is the maximum speed, right? So maximum speed of electrons and lambda is the wavelength of incident radiation. Yes. Using this graph and Einstein's photoelectric equation, obtain expression for Planck's constant and work function. Yes. Planck's constant and work function. That is what we have to find out from this particular graph. See, no numerical values given. So we will get some like expression for h, Planck's constant, and some expression for like work function also. These are the two quantities to be calculated. See, first of all, let us analyze this one. Vm versus 1 by lambda graph. It is a straight line given, right? It's a straight line given. So we have to check what will be its slope, what could be its y-intercept. All these things we have to check. For that, let us write down the equation. Einstein's photoelectric equation. What is it? Kinetic energy max is equal to energy of incident radiation minus the work function, correct? H nu minus W naught. That is Einstein's photoelectric equation. We need V max square, maximum velocity square. kinetic energy maximum can be represented as like half into mass into V max square, correct? Yes, is equal to, see, the frequency is not given, you are given in terms of lambda of incident radiation. This is frequency of incident radiation, but we need expression in terms of wavelength. So we will write hc by lambda instead, right? hc by lambda minus work function, correct? And now look at this. What will be Vm square? If you take Vm square from this, taking m by 2 to the other side. So 2 is going to the numerator, 2 into hc divided by m into lambda, right? 1 by lambda, right? Minus 2 goes to the numerator, 2 w naught divided by m. So this is the equation for V max square, a modified form of this equation now, right? So what are the changes we made? Kinetic energy represented as half mv max square, right? Because it's the maximum kinetic energy. And instead of frequency, we wrote like in terms of wavelength. Now look at this. These terms completely be a constant. For a given photosensitive material, work function is a constant. Mass of emitted photoelectrons is a constant. See, 2hc by m are constants. So we can say Vm square, correct? Vm square. What is our conclusion? Vm square is directly proportional to 1 by lambda, correct? Only lambda is a variable here. So 2hc by m is a constant. This is the relation between V max and lambda. That is why we got a straight line here, right? The graph is a straight line. Fine. What is the equation for a straight line? We know y is equal to mx plus c. mx plus c. That will help you to find out the unknown values now. Look at this. What is taken along x-axis? 1 by lambda. So instead of x, we have 1 by lambda, correct? 1 by lambda. Everything else in this term is m. m is a slope, correct? So whatever comes other than 1 by lambda is the slope. Now look at this. Y-intercept c is 2w naught by m. So we got y-intercept and let me take y-intercept as y naught or something, okay? Y naught is the y-intercept and slope of the graph is m. Then how will you find slope of the graph? Now look at the graph once again. See, you are given one angle theta here. If you know that angle theta, how will you find the slope of the graph? M, which is slope of the graph, is either y2 minus y1 divided by x2 minus x1, right? Change in y-axis by change in x-axis. Or it is tangent of the angle between the graph and x-axis. That angle is marked in the diagram. See, tangent of this angle, angle between graph and x-axis. So tan theta is a slope, correct? Yes. So then I will equate tan theta is equal to, which is m, is equal to 2hc by m, and we can find out h from that, because the first quantity we have to find out is Planck's constant. Okay, so how will you find the Planck's constant? For that, we will go for the slope of the graph. We found slope of the graph, which is m, right? M is given as, from the graph, we found slope of the graph as tan theta. From the expression, we found slope as 2hc by m. Yes. See, slope is also equal to what? C by m. How did you get that? For that, we wrote the equation in terms of Vm square. And 1 by lambda is along x-axis. So instead of x, it is 1 by lambda. What comes other than that is the m slope. So 2hc by m. We got that value. See, you can equate these two. What is 2hc by m? Is going to be tan theta, right? Therefore, 2hc by m is tan theta. What is h? The Planck's constant is going to be m tan theta divided by 2c. That is the answer for the first question. That is what I told you. No numerical values, right? Nothing is given. Just some expression is obtained for Planck's constant. Okay, fine. So that is what we got from the first part of the question. Now, the second part is to find out the work function. So tell me what to do. We can go for the y-intercept now. y-intercept is c, which I am taking as y0, for example, that y0 is minus 2 omega naught by m. So we can say y-intercept of the graph. See, Planck's constant we already found out. That was the first part of the question. Now the second part of the question is to find out work function. Okay, for finding work function, y-intercept of the graph is equal to, tell me what is that value we obtained? It is 2 omega naught by m. Yes, actually 2 w naught, right? 2 w naught by m. But w naught is a work function, yes. So what is w naught? W naught is equal to m into y naught divided by 2. What is that y naught? Check the graph once again. What is that y naught? That's a y-intercept, right? The point where the graph strikes on y-axis. So y naught is called y-intercept. Okay, so we got work function expression also. So Planck's constant and work function in terms of, see, the quantities given in the graph with the help of Einstein's photoelectric equation. See, the question was about find maximum speed, everything is given. Using this graph and Einstein's photoelectric equation, obtain Planck's constant and work function. So we completely answered the question now. Yes. Okay, moving on to the next. Question number 6. Okay, again, a graph question, a straight line graph also. De Broglie wavelength lambda as a function of 1 by root of k. 1 by root of k. What could be that k? Kinetic energy, yes. For two particles of masses m1 and m2 are shown in the figure where k is the energy. That is the kinetic energy basically, yes, of the moving particles. See, that is the graph given. Lambda versus 1 by root of k. Okay, now the question is, what does the slope of the line represent? Yes, we have to find out the slope of the graph. Okay, that's the first question. Which of the two particles is heavier? Which of the two particles is heavier? That is what we have to identify from the second part. And the third part of the question, is this graph also valid for photon? See, photon. We'll come to that, okay? So first one, what is the relation between lambda and 1 by k? The graph stays, they are directly proportional, right? That is why the graph is a straight line. So let us actually find out what is that exact relation. Lambda is equal to, we know, if they have same two masses, right? Masses m1 and m2, kinetic energy. So which equation of de Broglie wavelength is to be used? Lambda in terms of kinetic energy and mass. So h divided by 2mk, right? Root of 2mk, where k is the kinetic energy. See, h, 2 and m, mass, are constants. So we can say lambda is inversely proportional to kinetic energy, or we can say lambda is proportional to 1 by root of k. Yes, lambda is proportional to 1 by root of k. That is why lambda 1 by root of k graph is a straight line. Yes, that is true. Now, what will be the slope of the graph? What will be the slope? How will you find out the slope of the graph? We know slope of any given graph, we just explained in the previous question. It can be either y2 minus y1 by x2 minus x1, change in y by change in x-axis, rise by run, 0. Or it could be tan theta, right? Yes. So here angle is not given. So I am going for y-axis by x-axis, y by x. What is taken along y-axis? It is lambda, wavelength lambda is taken. And what is taken along x-axis? 1 by root of k. If it is 1 by root of k, that root of k comes to the numerator, we get lambda times root k, correct? See, slope of the given graph is equal to lambda times root k, root kinetic energy. One more thing. What will be lambda times root k from this equation? Like, you know, the de Broglie's equation, standard form. If you take lambda and root k to the LHS, remaining terms like it will be h divided by 2m, square root of 2m, correct? I have taken this k, just that k into the LHS. See, h is a numerical constant, 2 is a constant, so we can take m. Lambda times root of k is inversely proportional to m. See, two vital informations we got. One, lambda root of k is inversely proportional to the mass. lambda root of k represents the slope of the graph, correct? So now we can combine them together. What can I write? Slope of this graph is actually, see, slope of the graph, which is lambda times root of k, is proportional to 1 by m. So slope is proportional to 1 by m. Right? So what does, 1 by root of m, right? Okay. You have to keep that square root. There's a square root here. So it will be square root here also. 1 by root of m. So what does the slope signify? You know, that was the first question. Slope of the graph represents, we already answered that part here. You know, question number 1, slope of the graph is the product of lambda times root of kinetic energy, which is actually equal to h by root of 2m. This is the answer for the first part of the question. Okay, so question number 1, we answered question number 1. Slope is equal to lambda times root of k, which is h by root of 2m. We scored 1 mark. Okay, now look at the second part of the question. Second part of the question says which of the two particles is heavier? Now we can easily identify that. See, we got slope is directly proportional to, right? Slope is directly proportional to 1 by root of m. That is our conclusion from the previous discussion. Slope is still proportional to 1 by root of m, which means if, you know, mass is greater, slope will be less. You are asked to identify which one is heavier, you know, heavier, m1 or m2. Look at the graph. See, slope of m2 is more than slope of m1, correct? Yes, we need heavier one. Heavier one will have a lesser slope, right? Because as per the relation, slope less means more mass. Yes, so which of the graph represents lesser slope? m1. Yes, so we can say m1 is greater than m2 because slope of m1 is less than slope of m2. From this relation, greater the mass, less the slope. So heavier one. Which is heavier? m1 is heavier, right? The first particle is heavier. Correct? Yes. So we answered the first two sub-questions of the question. Now we have only one more part remaining. You are asked to check, is this graph also valid for a photon? You know, justify your answer in each case. See, we know lambda is for the particle behaves like a wave, you know, matter waves, de Broglie waves. And for photon, this is not valid. You know, lambda is equal to h by p is not valid for like photons. No, it is not, because its momentum is not calculated like this. We have E is equal to hc by lambda. This is how we find wavelength of the photon, right? Lambda is equal to hc by E. This is how we represent or calculate the wavelength of the photon. See, for photon, this is not valid. So your answer should be no, we can't. Okay, that is not possible. Yes, fine. Then next question. Question number 7. Light of wavelength 600 nanometer is incident on a potassium. Work function 2.3 electron volt. Will photo emission of electrons occur? Yes, we have to check whether it is possible or not. What is the longest wavelength that will cause photo emission of electrons? Longest wavelength is the shortest frequency, right? So we are asked to find out the threshold wavelength. We had a discussion about this in the previous video, right, where we discussed MCQ questions. And also this part we explained in detail there, right? Look at the question, last part of the question, you're given some hint. Take HC as 1240 EV dot NM. NM is a nanometer, right? Yes. So we can use that equation. Here we know incident wavelength is given in nanometers only. If it is in nanometer, we did similar questions. So many questions in the MCQ discussion video. So that is 1240 to be used, right? Were 1240 to be used or 12400 to be used and all. Okay, so work function is given as 2.3 electron volt. See, so this is work function is actually the minimum frequency, minimum energy required to release electron from the metal surface. So this is the minimum energy required. The incident radiation at least should have this much energy, right? That is how we explained work function. Right, now let us check what will be energy of this radiation. We can use E is equal to, yes, E is equal to hc by lambda, and C, you are given hc as 1240 divided by wavelength in nanometer. It is given in nanometer only, so 1240 divided by 600, and that value is going to be equal to some 2.06 electron volt. Okay, 2.06 electron volt is the energy of that particular incoming radiation. Can it emit electrons from the metal surface? No, because the minimum energy required to release electron from the metal surface for that particular material is 2.3 electron volt. So at least 2.3 is required. How much we got? Only 2.06. So the answer is C. Answer for that part of the question, first part of the question, is no. No photoelectric emission possible, right? Because incident energy is less than the work function. Incident energy is less than what? The work function. So no photoelectric emission is possible. Now the second part of the question is about what is the longest wavelength that will cause emission of electrons. Longest wavelength is nothing but threshold wavelength, correct? Threshold wavelength. We know how to calculate threshold wavelength. We know the threshold, energy, work function is given. Work function is equal to h nu naught, which is equal to hc by lambda naught. Lambda naught is a threshold wavelength. How will you find out lambda naught from this? Lambda naught is going to be hc divided by the work function. See, we can use the same relation here. You are given work function in electron volt, right? Work function in electron volt. So this could be 1240 divided by wavelength in nanometer. So if you want to get lambda naught in nanometer, remember it is in nanometer, is equal to hc. See, here hc can be 1240 divided by what is the work function in electron volt? It is 2.3. Yes, that value is given as 2.3. Okay, remember that value will be obtained in nanometers because we have used 1240 value here. And if you simplify this, you will get lambda naught is equal to 539.1 nanometers. That is a threshold wavelength of that particular metal surface. Okay, fine. So that was an easy one. Next question. A proton and an alpha particle are accelerated through different potentials V1 and V2 respectively so that they have same de Broglie wavelengths. Yes, see, V1 is a accelerating potential for the first one. V2 is that for the second. So that question there itself gives you a hint which equation for de Broglie wavelength is to be used. We know lambda is equal to h divided by root of 2mq into v, right? The equation in which we have the accelerating potential. This is the only equation we have accelerating potential involved, right? Yes. So this equation is to be used. We have proton and alpha particle. So look at this. For proton and alpha particle, h remains the same. 2 is also remains the same. Their potentials are like, V1 and V2. Question also says they have same de Broglie wavelength. See, they have same de Broglie wavelength. Then lambda of P and lambda of alpha can be equated. See, we can say lambda of P could be proportional to 1 by root of mass of proton, see, charge of proton and accelerating potential of proton. It is V1. See, accelerating potential of proton is V1. For alpha particle, it is V2. So how will you write the same for alpha particle? Lambda alpha is equal to, is proportional to 1 by root of mass of alpha, charge of alpha and V2. Okay, so lambda P and lambda alpha. We formed equations and it is given that, what is given in the question? Given that lambda P is equal to lambda alpha. So if you take the ratio of these equations, suppose this is my equation number 1, this equation number 2, what will be that? Lambda P divided by lambda alpha, taking the ratio, is equal to, see, the ratio will be just the other way around, right? Root of mass of alpha, charge of alpha, V2, divided by root of mass of proton, charge of proton, and V1. Correct? And lambda p by lambda alpha is going to be 1 because the question says lambda p is equal to lambda alpha. So we can just cross multiply this. What will you get? Root of mass of proton, charge of proton, accelerating potential of proton is equal to root of mass of alpha, charge of alpha, and V2. Squaring on either side, what happens? Both squares will be, square root will be gone. Now, mass of proton. We know we used the same in a question before. Mass of proton is equal to 1 atomic mass unit, and mass of alpha particle is going to be 4 atomic mass unit. What will be charge of proton? Q of proton is just 1 E. One proton has E charge, but charge of alpha particle is going to be 2E, right? Because 2 protons and 2 neutrons also, they are chargeless, we know. So then mass of proton is going to be U. See, square root is already gone. We squared, okay? So we got MP as U into E into V1 is equal to mass of alpha is 4 atomic mass unit, 2E into what? Into V2. So now we can cancel those terms. E gets cancelled, U gets cancelled. We need V1 by V2. Take that V2 to the other side. What is V1 by V2? We have 8. 8:1. And that is our final answer. Okay. So we just compared alpha particle and proton. If you know the features of alpha particle and proton properly, and if you know this equation, you can easily get that ratio. Okay, fine. Moving on to the next question. Consider a neutron of mass m, of kinetic energy E, and a photon of the same energy. Let lambda n, lambda p be the de Broglie wavelength of neutron and the wavelength of photon respectively. Okay, obtain expression for lambda n by lambda p. See, don't be confused here. Lambda p is not proton, it is a photon. Read the question properly. It is a photon, correct? But n stands for a neutron. So one should be de Broglie equation, the other one should be the lambda equation in terms of energy, right? Yes, we had a similar question before. Can we apply the same equation for photon or not, right? What was our conclusion? We said no, we cannot. So here we have to compare two wavelengths, given that both photon and photon and neutron, see, both of them have the same kinetic energy, okay? Same kinetic energy for both. So the equation in terms of kinetic energy we are going to take, lambda is equal to, see, for neutron, let us go for neutron first. We know lambda of neutron is equal to h by root of what? Root of, it is given in terms of kinetic energy and mass. So we can go for 2m into E, correct? Kinetic energy E. Okay. See, this is the expression for lambda n. Now, what could be photon? For photon, what is the wavelength? Lambda p. Remember, it is a photon, okay, not proton, photon. We know for a photon, energy E is calculated as hc by lambda. H nu, right? But in terms of lambda, we need, because lambda n is to be taken. So, E is equal to hc by lambda. How will you find lambda from this? E divided by hc. Yes. So, lambda p is going to be E. The same kinetic energy. See, both of them have same kinetic energy. So, same E I can use. E divided by, hc divided by E. Correct? Lambda p is going to be equal to hc divided by E. Equation number 1 and equation number 2. Just take the ratio of these two equations, you will get the final answer. See, lambda n by lambda p. That's it. So, equation number 1 divided by equation number 2, we get lambda n by lambda p, and lambda n is going to be h divided by root of 2m into E, the whole divided by, wait, we have to take, lambda n by lambda p only. So, now lambda p is going to be hc divided by E. So, we can cancel h from both the sides, and E is coming up. So E divided by root of 2m into E into C. Correct? So if you include this E into the square root, we can write this like E square, taking the square root of the whole terms, okay? E square divided by 2me into C square, correct? Right. I'm just going to simplify this E and root E, that's it. So now we can cancel one of the E's inside, E gets cancelled. What is the final answer? We got lambda n by lambda p is equal to the whole square root of E divided by 2mc square. That is the required ratio of wavelength of neutron to the wavelength of photon given. They have same energy. That is why we could cancel that E from the calculation. This E and this E cancels. One was for proton. No, one was for neutron and the other one was photon, right? They have same energy. That is how we cancelled it. Okay. So again, we had a same concept in another question. So it's fine. Another one. Light of wavelength 500 nanometer is incident on a cesium metal. Work function is 2.14 electron volt. Okay. And photo emission of electrons occurs. Yes. So photoelectric effect is happening. Calculate kinetic energy of the fastest electron. See, you're asked to find out kinetic energy max. Energy of incoming radiation minus work function. Einstein's photoelectric equation. Stopping potential for this situation. See, if you know kinetic energy, yes, in the previous discussion, like in the MCQ discussion of the same chapter, we discussed how stopping potential is related to kinetic energy, right? Yes. So kinetic energy is equal to E minus work function. We calculate the first part. Kinetic energy is to be calculated. For that, work function is given. Incident energy is given in terms of lambda. Lambda is in nanometers, right? So we know E is equal to hc by lambda minus work function. See, kinetic energy we can calculate in electron volt. It's fine. So we have to find this in electron volt. This is already in electron volt. Some 2.14 is given. So we know how to calculate this, right? Wavelength is given in nanometers. We discussed that before, right? Nanometer is if the value, then it is 1240 divided by wavelength in nanometer, which is 500, correct? 1240 divided by 500 minus what? 2.14 electron volt. Yes. That will be the kinetic energy maximum. Kinetic energy maximum is obtained from this one. So we get this as 2.48, right? 1240 divided by 500. Minus, see, that is going to be double of 1240, right? That is 2.48. Minus 2.14. Okay. So that difference is going to be the kinetic energy. And how will you find out the stopping potential? We know second part of the question was to find the stopping potential. Stopping potential is E into V naught is equal to kinetic energy, right? Kinetic energy is equal to E into V naught. So if you know the kinetic energy in electron volt, whatever comes here, so kinetic energy in electron volt, okay, I'll just go for that value, 2.48 minus 2.14, whatever it may be, you just simplify. That will be equal to E, that much electron volt. Wait, that much electron volt is equal to E into V naught, correct? Yes. So if you want to get stopping potential in SI unit, V naught is stopping potential, we have to get that value in volt. Volt is an SI unit, right? We discussed this in the other video. Yes. So then we have to convert this into joules. So 2.48 minus 2.14 into what? 1.6 into 10 raised to minus 19 is equal to what? E into V naught. Then what did we do? We cancelled that E and 1.6, right? So whatever be your kinetic energy in electron volt, without that E, if you write, that will be your stopping potential. So this much electron volt is the kinetic energy maximum, right? This much electron volt you have kinetic energy maximum, and stopping potential will be the same value, 2.48 minus 2.14, but the unit will be what? Volt. That is the stopping potential. As simple as that. Just cut that E, then that will be converted to stopping potential. That is what we discussed in detail, right, before. Fine. So these are some questions, 2 more questions we got from dual nature of matter and radiation, and we will meet with another video later. Thank you.